Hello, let's start with digital fundamentals for computer architecture. Before starting with this lecture, please go through the basics of digital electronics, which is basically the basics of digital gates, combinational circuits. Sequential circuits are not required for this particular portion. So basically, logic gates, the concept of truth tables, combinational circuits, and Boolean expressions. Okay, let's start. So the first topic or first element that we'll be covering is multiplexers. Okay. So multiplexer is basically a device which has a certain number of inputs but only one output. And how it works is that at any given point of time, one of these inputs will be transferred to the output. Any one of these inputs can be transferred to the output. Which input is being transferred to the output depends on this thing, which is the select lines. And this select lines can be a certain number of bits. Okay. So let's see an example here. In this truth table, we are taking the select lines to have 3 bits, right? So it can have a combination from 000 to 111, that is 8 combinations. So basically what is happening, we can use these 8 combinations of select lines to choose from how many? 8 input lines, and out of these 8 input lines, depending on the value or the particular combination of the select line, one input value will be transferred to the output. So that is this truth table. So remember, in general there can be n select lines. Always there will be only one in output line, but there will be, if there are n select lines, there will be 2 to the power of n input lines. So this is the main thing that you have to remember for multiplexers. The next device that we are going to deal with is called a decoder. Right. Decoder is a device which converts input of, say, n inputs into m outputs. N inputs into m outputs. Okay. So let's see the concept with an example here. Consider this truth table. A2, A1, A0 are the 3 input lines. Okay. And here there are how many? 8 output lines, y0 to y7. So if we generalize, so this is what? 3 input lines and 8, which is 2 to the power of 3 output lines. So n input lines and 2 to the power of n output lines. So let's see how this is happening. So depending on the value of the input lines, one and only one of the output lines will be high. Right. Here for the input combination of 000, the output y0 is 1, and for the input combination of 010, the output y2 is high, and the rest is always 0 or low. So we can see a pattern here. What is the pattern? This 3-bit combination represents a binary number, and the output corresponding to that input binary combination corresponds to the decimal value of that binary number that we are giving as input. So here 010 corresponds to an output of y2, right? So binary combination of 010 is converted to decimal value of 2, or binary code is decoded into decimal. That is where the name comes from. It is for decoding binary into decimal. So the thing to remember here is it decodes binary value in the input to a decimal value in the output, and for n input lines there will be 2 to the power of n output lines. Okay, the next topic that we'll be seeing is adders, and we'll be seeing some number of adders, but let's start from the basics. Okay, the first thing, the most fundamental building block of an adder that we can call as a half adder. So half adder is an adder which takes in 2 input bits and gives out 2 output bits. So the 2 input bits here will be A and B, and the 2 output bits are the sum bit and the carry out bit. Okay, so this is basic binary addition, 1 bit single bit binary addition, and the expression for the sum bit is A XOR B, and the expression for the carry out bit is A and B. The next thing is a full adder, which is basically an extension of a half adder, as the name suggests actually. So here the thing is that the full adder has the capability to consider a carry from a previous stage of an addition. In half adder it was not there actually. In a half adder it could only add 2 bits. Here also the full adder can add only 2 bits, but it can consider a carry in from a previous stage of an addition. Like the previous one, there are 2 outputs, sum and carry. So this is the truth table, and from this truth table, using Carnot map method, we can come to the expression for the sum, which is A XOR B XOR C in, and the expression for C out, AB or A and B or A and C in or B and C in. Right, pretty basic stuff. So now moving on, the next one, triple carry adder. Okay, now till now these two, half adder and full adder, were sort of prototypes. They were not much useful in the sense that they could just add single bits. In a real life scenario, single bit addition are not enough, and we'll have to add maybe 8 bits, 4 bits, 8 bits, 16 bits, 32 bits, 64 bits, like that. So for that we are using a triple carry adder. So please be careful when you're seeing the notation here. So when you look at the notation, it looks similar. Actually the notation is pretty much the same. Adder has this notation with the plus sign. The difference is that the input lines and output lines will be different. Here this notation is used to show that it is an n bit input. Here also it is an n bit input, and here it is an n bit output. Right. So let's see how the ripple carry adder is implemented. So ripple carry adder is nothing but a cascading of full adders. So this first full adder is used to add the first bits, the LSBs of the 2 numbers, along with the carry in, which you can give as 0, or if there is any carry from the previous sum, you can use that. From this there will be carry out, which is given to the carry in of the next stage. This will be adding A1 B1, which is the bit next to the or just higher to the LSB, and so on and so forth till the MSB, and the output of this MSB will be what, the final bit, and there will be the carry out, which is the final carry of the whole addition. This is an example of a 32-bit ripple carry. Okay, so why does this name ripple carry adder come? The thing is that here the carry is being rippled through the adders, right, from the beginning, from the LSB to the MSB stage of the addition. The carry is being rippled one by one. It is going, that is, for this particular stage, for let's say the ith stage to function, the carry from the I minus 1 stage should be there. So for each stage to function, the carry from the previous stage has to be there. So that rippling of carry is why this adder gets the ripple carry adder name. But the problem here is, because of this nature of rippling of the carry, this is a slow adder. Okay, if there are n bits or n stages of a full adder, the total time period or time delay is n into time for a single full adder. Okay, so ripple carry adder is a solution for multiple bit addition, but it is not an efficient one. So let's look at a slightly improved version, carry look ahead adder. Okay, again carry look ahead adder also uses full adders. See, carry look ahead adder also uses full adders for its implementation, but it will have some extra logic. So what was the major flaw with ripple carry adder? It was that each stage had to wait for the previous stage to give the carry, then only it could do the addition, right? So in this one, in carry look ahead adder, that process is eliminated. That is, that waiting for that carry from the previous stage is eliminated, and the carry for each stage is generated early on, right? That is from where this usage of look ahead comes from. Okay, carry is being generated ahead. So to understand the basic concept of that, let's see how this thing works, starting from a single full adder, right? Okay, so as we mentioned earlier, full adder is an adder which takes in 2 bits to be added. Also it can take in a carry, right? And it gives a carry out and a sum. So with this, let's see, or let's find some patterns. So first let's look at the red portions marked in the truth table using red ink. Okay, here if you see, A and B are 1, right? A equal to 1, B equal to 1. Let's not consider the sum here. Sum is irrelevant as far as the logic of the carry is here concerned. Let's just look at A, B, C in and C out. Okay, A equal to 1, B equal to 1, A equal to 1, B equal to 1. And if you see here C in is 0, here C in is 1. But here C out is 1, C out is 1. That is, irrespective of C in, if A and B both are 1s, irrespective of C in, there will be a carry out. That is, essentially a carry is being generated at this point. That is, if A and B, both A and B are 1s, carry is being generated. This condition is called a condition for generation of carry. So if A and B are 1s, C out is 1, irrespective of the value of C in. That is, for an ith stage, we define this term GI equal to AI and BI. GI will be 1 only if both A and B are 1. Okay, irrespective of C in, there will be a C out. Now let's see the ones marked with black. Okay, here if you see the pattern of A and B, here A is 0, B is 1, A is 1, B is 0, here A is 0, B is 1, A is 1, B is 0. That is, here either A or B is 1 but not both, right? Either A is 1 and B is 0, or A is 0 and B is 1. That is the condition that we are looking at. At this point, if you see here, C in is 0, C out is 0. Here C in is 1, C out is 1. So what is happening? Whatever is the C in, it is being directly transferred as C out, or whatever is C in, it is being propagated as C out. This condition is called a condition for carry propagate. Earlier it was condition for carry generate, because irrespective of the input carry, a carry is being generated at the output. But here it is not like that. Depending on whether there is whatever carry comes into the adder, it is being propagated to the output. So if either A or B is 1, C out equal to C in. That is the condition for carry propagate, and we define the term PI equal to AI or BI. This I is standing for ith stage. Okay. The last condition is the one marked blue. So it is what is it? It is for A equal to 0 and B equal to 0. It doesn't matter what C in is, C out is 0. This is not of interest for us because we are trying to predict when a carry is required for a ith stage, and so we are only interested in the condition when there is carry, which is definitely when there is a generation condition and when a carry is being propagated. So we are only considering these two things, and this is irrelevant anyway, it doesn't make a difference. So let's see the condition for C out at any given stage. So the carry at, let's see this one here, right? So the carry at any given stage, ith stage, will be 1 if either Gi is 1, right? If Gi is 1, that is, if there is a carry being generated, then definitely there will be a carry at the output. Or if there is a carry being propagated, if there is a carry being coming into the adder as a Cin, then it will be propagated, right? So the condition for a carry out for an ith stage is if there is a generation or if there is a propagation, that is Ci equal to Gi or Pi and Ci minus 1. Here we are just expanding the definitions of Gi and Pi. So Ci equals Ai and Bi, or Ai or Bi and Ci minus 1. This is the Gi term, this is the Pi term. So the advantage is that because we are generating carry for each stage, there is no need for rippling of carry from the previous stage, so on and so forth. So there isn't much delay. Delay is reduced by a lot. So let's consider an example for a 4-bit carry look ahead adder, CLA. So these are the expanded equations for each stage, for each carry C0, which is G0 plus P0 Cin. Cin is the carry which we are giving in the beginning. So A0, B0 plus or A0 or B0 and Cin. C1 is G1 plus P1 C0. Here for C0 we'll be substituting from here, right? So it will be G1 plus P1 and G0, this one, G0 or P0 C1, which again we can expand to our requirement. For C2 it will be G2 plus P2 C1. So it will be what? A2 B2 or A1 or B2 into this term, like that. C3 again. So the thing is that this is getting more and more complex, right? So what is the purpose of writing these equations? It is to implement it using logic gates. So we want to get, the idea is that we want to get the carry for each stage at the same time, so that we can, first of all we can reduce the time and we can get the carry at the same time, and therefore we can get the sum at the same time. But here if you see, even for this 4-bit carry look ahead adder, the complexity of the equations are getting bigger, and the levels of logic gates required to implement is getting more and more. So there will be hazards, a chance of hazards are there. So usually what happens is that we stop implementing a carry look ahead adder for 4 bits. So here this is how it is done. These equations, these 4 equations are implemented in this carry generation logic, which will have inputs A3 to A0, B3 to B0 and Cin. From this carry generation logic, carries are generated directly and given to the respective full adders, and the full adders are given the inputs, the numbers to be added, bits to be, corresponding bits to be added, and we get the sum. This is a 4-bit carry look ahead adder. Okay, so like I mentioned earlier, this equation is getting complex, so even for a 4-bit carry look ahead adder. So if we want to implement this carry look ahead adder for, let's say, 32-bit and addition, like we are like this equation given here, we don't go for a 32-bit carry look ahead adder. Instead we cascade 8 4-bit carry look ahead adders, right? So A3 to A0 and B3 to B0 will be given to this 4-bit block, and A7 to A4 and B7 to B4 will be given to this block, and like that up to A31 to A28 and B31 to B28 into the last block, right? So here what is happening is that even though a carry look ahead logic is being implemented for this 4-bit carry look ahead adder block, there is a rippling of carry from block to block, right? So yes, we can reduce the time delay required for this addition compared to a simple ripple carry adder, but still here there will be a considerable amount of delay. So to solve this problem, we will consider the next or slightly fast adder, which is a prefix adder.